The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Today's lecture is not mathematically hard, but it's really important to establish vocabulary today. We're going to talk about vibration for the rest of the term. And vibration is essentially applied dynamics. So up until now, we've been finding equations of motion, but not solving them. Did you notice that? I've almost never asked you to solve the equation of motion that you've just discovered using Lagrange or whatever. The rest of the term, we're actually going to be talking mostly about the resulting motion. The equations of motion are pretty easy to find. You have all the techniques that you need to know for finding them. And now we're going to talk about how things vibrate. So why do we choose vibration? Vibration is an incredibly common phenomenon. We wouldn't have speech without vibration. You wouldn't have musical instruments without vibration. It's a positive thing when it's making good music. It's a negative thing when it's keeping you awake at night because the air conditioner in the next room is causing something to rattle in the room and it's driving you nuts. So it's good. You can want it, it can be desirable, and you can not want it. And you need to know ways of getting rid of it. And so we're going to talk about vibration, about making vibration, about suppressing vibration, about isolating sensitive instruments from the vibration of the floor, things like that. So that's the topic of the rest of the term. And today we're going to talk about single degree of freedom systems. And you might think that we're spending an awful lot of time on single degree freedom systems. But there's a reason for that. Lots of things in real life, like this is just an aluminum rod. This will vibrate. And continuous systems, which this is, have a theoretically infinite number of degrees of freedom. Yet, when it comes to talking about its vibration, it is conceptually easy to think about the vibration of an object like this, one natural frequency, one natural mode at a time. And in fact, you can model that natural mode with its single degree of freedom equivalent. And that's the way I approach vibration. So if you can isolate one particular mode, you can literally model it as a mass spring dashpot. So you need to understand the mass spring dashpot behavior inside and out. Okay, because it's the vocabulary we use to do much more complicated things. So single degree of freedom system, like the simple pendulum, has a natural frequency. In this case, has a mode shape. Here's another one, kind of fun. Single degree of freedom. This obviously involves rotation. And you can figure that out using Lagrange or whatever. Single degree of freedom systems. But now I'm going to excite one mode of vibration of this. Hear the real high pitch? Get it down here by the mic so the people at home can hear it. About 1 kilohertz, way up there. And that's one natural mode of this thing in longitudinal vibration. When I thump it sideways, you hear a lower tone. Hear that? Rather than, That's bending vibration of this thing. But each mode of vibration I can think of in terms of its equivalent single degree of freedom oscillator. So we'll get to talking about these things a little bit, continuous systems, in the last couple lectures of the term. But for today, then, we're really going to develop this vocabulary around the vibration of single degree of freedom systems. So let's start. All right. So to keep it from being totally boring, I'm going to start with a little mass spring dashpot that has two springs. And they're of such a length that unstretched, they just meet in the middle. And then I'm going to take a mass and I'm going to squeeze it in between these two springs. I can't draw a spring very well today. And this is K1, and this is K2, and here's M. And we'll put it on roller so it's obviously constrained to motion in one direction. And I'll pick this point here as the place I'm going to put my inertial coordinate. So my inertial coordinate is just measured from where happens to be where the endpoints of these two springs were. Now, to squeeze this spring in here, there's clearly pre-compression in these springs. So we are no longer at a zero force state, right? So, and I want to get the equations of motion in this, and moreover, I want to find out what's the natural frequency of this spring. So let's check your intuition. So write down on your piece of paper whether or not the natural frequency will be different because there's pre-compression, or whether or not that pre-compression in the springs has nothing to do with the natural frequency. So write down on your paper, natural frequency is different or natural frequency is the same. Let's have a prediction here. And then we'll set about figuring this out, and in the course of doing it, we'll develop a little vocabulary. We've, all through the course so far, when we've done equations of motion, we've usually picked, the zero spring force position. And we sort of led you down this rosy path that suggests, that's the way we do it. But there are other ways that you're going to find that are preferable to that sometimes. So that's one of the reasons I'm doing this example. So let's do a free body diagram. And if I held this mass, for example, right at the center when I put the springs in, it's obvious that this spring gets compressed by half of the length of the mass, and this spring gets compressed by half of the length of the mass, right? So this is going to be L long. So if I held it right in the middle, it would compress L over 2 and L over 2. But then when I release it, if these springs are of different spring constant, it's going to move a little bit. So the force on this side pushing back is some K1 times L over 2 minus the distance that I move in that direction, which would relieve it. And the force on this side also pushes back. It's K2 times L2 over 2 plus X, because when I go in that direction, I'm compressing it even further. And those are the total forces in the X direction on this body. There's an N and an mg, which we know we don't have to deal with because we're only interested in motion left and right. All right, so we can say sum of the forces in the X direction, mass times the acceleration, and those forces are K1 L2 minus X minus K2 L over 2 plus X. And that's the complete equation of motion for this problem. Okay. I'm going to rearrange it so that I get the functions of X together here. So mx double dot plus K1 plus K2 times X equals L over 2 times K1 minus K2. And that's your equation of motion. It's non-homogeneous. This is all constants on the right-hand side. And on the left-hand side are the functions of x, stuff that's functions of x, right? So what's the natural frequency of the system? I hear a square root of the quantity K1 plus K2, the stiffness, divided by m. You know, K over m, usual mass spring dashpot system. Did the precompression have anything to do with the natural frequency? I won't ask you to embarrass yourselves, but a few of you probably got that wrong, right? So there's a lesson in this and that I want you to go away with, and we'll go and I'll say it once, and that is when an external force has nothing to do with the motion coordinates in the problem, it doesn't affect the natural frequency. These come from external forces. These are these precompressions, right? And I can separate them out. And they are not functions of x. The stuff on the right-hand side of the equation that's not function of the motion variable cannot affect the natural frequency. Okay, so I'll give you another one. This is our common thing hanging from a stick. So I've taken my system that I built the other day for a different purpose, but now it's just a mass hanging from a spring, and it's right now at its equilibrium position. Are the forces, and there's non-zero force in the spring. It clearly has a natural frequency. And is that natural frequency a function of gravity? And so if you go to write the equations of motion of this system, you would find mx double dot plus kx equals mg, but the mg is not a function of x. The natural frequency is, again, square root of k over m. Okay. Now, we want to talk about solving this differential equation. And because it's got this constant term on the right-hand side, it's non-homogeneous, which is kind of a nuisance term in terms of dealing with the differential equation. It'd be a lot nicer if the right-hand side were 0. So I want to make the right-hand side of this one 0. And draw a useful conclusion from that. First thing I need to know is I'd like to know what is the static equilibrium position of this. And when you go to compute static equilibrium, you look at the equation of motion and say, make all motion variables things that are functions of time 0. So no acceleration, you're left with this. So you just solve this for whatever the value of x is, and I'll call it x sub s for x static. And you'll find that, oh, well, it's that term divided by k1 plus k2. K1 minus k2 all over K1 plus K2. And that's the static position. So now let's say, well, we started off with this motion variable that was arbitrarily defined at the middle. And let's say that, well, it's made up of a static component, which is a constant, just a value, plus a dynamic component I'll call x sub d, which moves. This is the function of time. This is a constant. It's not a function of time. And that means if I take its derivative, I might need a value for x dot. That goes away. It's just x d dot. And x double dot is x d double dot. And let's substitute this into my equation of motion. So it becomes m x d double dot plus k1 plus k2 times, and now this term has got two pieces now, times xd plus k1 plus k2 times xs equals L over 2 k1 minus k2. All right? Now, if I say, well, let's examine the static case, then this goes away. For the static equilibrium case, this term is 0, this term is 0, because the dynamic motion is 0 in the static case. This is motion about, that xd is motion about the static equilibrium position. So for static case, these two terms go away, and we know that this equals that. But if that's true, we can get rid of these. They cancel one another. So these terms cancel. And I'm left with mxd double dot plus k equivalent, I'll call it, xd equals 0. So the k equivalent is just the total stiffnesses in the system, whatever it works out, right? In this case, it's k1 plus k2. And the natural frequency, omega n, is the square root of k equivalent divided by m. So most often, when you're doing, if you're interested in vibration, you're interested in natural frequencies, you're interested in solving the differential equation, you will find it advantageous to write your equations of motion around the static equilibrium position. So I could have started this problem by saying, whatever the static equilibrium position is of this thing, that's what I'm measuring x from. And then I would have come to this equation eventually. You'd have to figure out what is the static equilibrium position and know what you're doing, but once you know it, then you have the answer. Now, the same thing is true of that problem. That's a non-homogeneous differential equation for the hanging mass. And we've derived the equations of motion things for this many different ways, this term, right? But we usually said zero spring force. But now, if you started from here and said, this is the static equilibrium position, what's the motion about this position? Then you'd get the equation with 0 on the right-hand side. Lots of advantages there to using that. Okay, once first, all single degree of freedom oscillators will boil down to this equation. This is one involving translation, but for a simple pendulum, this object, for example, is a pendulum, but it's a rotational, so it's a pendulum, but it's 1 degree of freedom. All pendulum problems, if you do them about equilibrium positions, boil down to some I with respect to the point that they're rocking about, theta double dot plus some kt torsional spring constant theta equals 0. They take the same form. So all translational single degree of freedom systems, all rotational single degree of freedom system, it's the same differential equation. Just this involves mass and linear acceleration. This involves mass, moment of inertia, and rotational acceleration. So everything that I say about the solution to single degree of freedom systems applies to both types of problems. So let's look into the solution of this equation briefly. Mostly I'm doing this to establish some terminology. So the solution, a solution, I know, or I can show, that xd of t, the solution to this problem, notice, are there any external forces, by the way, excitations, f of t's or anything? No. So this thing has no external excitation that's going to make it move. So its only source of vibration or motion is what? Comes from, I hear, initial conditions, right? You have to do something to perturb it, and then it'll vibrate. So here it is, it's about its equilibrium position. I give it an initial deflection and let go. Or it's around its initial condition, and I give it an initial velocity. It also responds, or some combination of the two. So initial conditions are the only things that account for motion of something without external excitation. And that motion, I can write that solution as a cosine omega t, you'll find is a possible solution. B sine omega t is another possible solution. Some a cosine omega t minus phase angles, also solution. And some a e to the I omega t you find is also a solution. Any of those things you can throw in, and the precise values of these things, the a's, the b's, the phi's, and so forth, depend on the initial conditions. Okay, so let's do this one quickly. All right. And I'll choose and I'm going to stop writing the S sub d here. This is now my position from the equilibrium point. So x of t, I'm going to say let it be an a1 cosine omega t plus a b1 sine omega t. I'm going to plug it in. When I plug it into the equation of motion, x double dot requires you to take two derivatives of each of these terms. Two derivatives of cosine gives you minus omega cosine. Two derivatives of sine, minus omega squared cosine, minus omega squared sine. So the answer comes out minus m omega squared plus k, equivalent here, times a1 cosine plus b1 sine, omega t's obviously in them, equals 0. So I've just plugged it into that equation of motion. I get this back. This is what I started with. That's x. In general, it is not equal to 0. It can take on all sorts of values. So that side, that's not generally 0, and that means this must be. And from this, then, when we solve this, we find that omega, what we call n squared, is k over m, and that's, of course, where our natural frequency comes from. This is called the undamped natural frequency. There's no damping in this problem yet. We get the square root of k over m is the natural frequency of the system. Okay, let's find out, but what are A1 and B1? Well, let's let x naught be x at t equals 0 here. And if we just plug that in here, put t equals 0 here, cosine goes to 1, this term goes away. So this implies that A1 equals x naught. So we find out right away that the A1 cosine omega t takes care of the response to an initial deflection. And we need a x dot here minus A1 omega sine omega t plus B1 omega cosine omega t. That's the derivative of x. We know the solution's that, so its first derivative, the velocity must look like this. And let's let v naught equals x dot at t equals 0. And we plug that in, this term goes away, and we get B1 omega, and cosine is 1. So therefore, B1 is V0 over omega, but in fact, the omega is omega n. Because it's that we already found out that the only frequency that satisfies the equation of motion when you have only initial conditions in the system, the only frequency that is allowed in the answer is the natural frequency. So we now know B1 is V naught over omega n, and A1 is x naught. So if I give you any combination of initial displacement and initial velocity, you can write out for me the exact time history of the motion. X naught, cosine omega t, plus V naught over omega n, sine omega t is the complete solution for a response to initial conditions. So any translational oscillator, 1 degree of freedom, where you have a translational coordinate, measured from its equilibrium position, has the equation of motion. Actually, we could write, you've done this enough, but if we added a force here and we added some damping, and I wanted the equation of motion of this, you know that it's mx double dot plus bx dot plus kx equals f of t. And so you'll often, you're going to be confronted with problems, find the equation of motion of the system. It comes up looking like that, and I say, what's the natural frequency? And I've been a little sloppy. I really mean, what's the undamped natural frequency? And so to find the undamped, when one says that, what's the undamped natural frequency? You just temporarily let B and F be 0, just temporarily. And solve then for omega n equals square root of k over m. That's what you do. And then, so we know this is a parameter that that tells us about the behavior of the system, which you always want to know for these single degree of freedom systems. What is the natural frequency of the system? Okay. And we know for b equals 0 and f of 0, then the response can be only due to initial conditions. So we have x of t we know is going to be some x naught cosine omega n t plus v0 over omega n sine omega n t. And every simple vibration system in the world behaves basically like this from initial conditions. It'll be some part responding to the initial displacement, some part to the initial velocity. And damping is going to make it a little bit more complex, but not actually by much. The same basic terms appear even when you have damping in it. This can be expressed as some A cosine omega, in this case nt, minus a phase angle. And it's useful to know this trigonometric identity to be able to put things together into an expression like that. And you'll find out that A is just the square root of the two pieces. It's a sine and cosine term, so you have an x naught squared plus a v0 over omega n squared square root. Remember, this is any a and b. It's just the square root of a squared plus b squared. That's what we're doing here. And the phase angle, the tangent inverse. If this were, I've been calling this like an A, and this is the B quantity. It's a tangent inverse of, get my signs right, B over A, which in this case then is tangent inverse of X v0 over x naught omega n. That's all there is to it. And finally, another trig thing that you need to know, we're going to use it quite a bit, is that if you have an expression A cosine omega t minus phi, that's equal to the real part of A e to the I omega t. Okay, and if A is real, then I don't want to write it that way. When A is real, then this is just the real, it's just the real part, it's A times e to the I omega t minus phi. Because Euler's formula says e to the I theta equals cosine theta plus I sine of theta. So if you have an I omega t minus phi here, you get back a cosine omega t minus phi and another term, an I sine omega t minus phi. So you can always express that as the real part of that. So we're going to need that little trig identity as we go through the term. Now, I found in many years of teaching vibration that something that many students find a little confusing is this notion of phase angle. What does phase angle really mean? So I'll try to explain it to you in a couple different ways. So let's look at what this vibration that we're talking about here, x naught cosine omega t plus v naught over omega n sine omega, what's it look like? So we've just got our, we see what it looks like, but if you plot the motion of this thing just versus time, what's it look like, and where does phase angle come into it? Well, this is now x of t, and this is t equals 0, and this undamped system is essentially going to look like that. And this is the value x naught, the amplitude, the initial condition on x that you began with. And right here, the slope, v naught, is the slope, the initial slope of this curve, right? Because the time derivative is of x dot. If we were plotting x dot, the initial velocity is omega x naught. And so it's just the slope is v naught here. So this is your initial velocity. This is the, and I didn't, yeah, that's right. This is the initial displacement. The total written out mathematically, it looks like that. And I'm plotting this function a cosine omega t minus phi. Yeah. I see a hand up.
Is x naught at t equals 0, or is it like a little bit after?
No, I was just looking at myself and said, this can't be right. This has got to be the initial condition on x, and this has to be the initial condition on v. And whatever this turns out to be, is whatever it turns out to be. You have some initial velocity, you have some initial displacement. The system can actually peak out sometime later at a maximum value, right? And that maximum value is that. So this is, this over here is the square root of x naught squared plus v0 over omega n squared square root. That's what the peak value is. And this system's undamped, so it just goes on forever. So the question is, though, what is this gap here between when it starts and when it makes its maximum? Well, you can, when we use an expression like we said we can express this as some a cosine omega t minus phi. It's just the point at which the cosine then reaches its maximum. So if this axis here is omega t, if we plot this actually versus omega t, then one full cycle here is 2 pi, or 360 degrees. So if you plot it versus omega t, then this gap in here is just phi. That's the delay in angle, if you will, that the system goes through between getting from the initial conditions to getting to the peak of the cosine. So, and phi must also then be equal to some omega n times a delta tau, I'll call it, some time delay. So if I plot, if this is plotted, if this axis is time, not omega t, but time, then this same plot, this delay here, this is a delta, this is a time delay. In this, when you plot it against time, it's a delay in time to get to the peak. And omega n delta tau, this delay, must be equal to the phase angle. So the delta tau, this time delay, is phi over omega n. So you can think about this as a delay in time or as a shift in phase angle, depending on whether or not you want to plot this thing as a function of omega t or as a function of time. But you're going to need this concept of phase angle the rest of the term. You want to ask any questions about phase? Well, the other, because we're doing vibration for the remainder of the term, the This is an introduction to a topic called linear systems. And so this is basically the fundamental stuff that in which you then, when you go on to 2004, which is controls and that sort of thing, this is the basic intro to it. Okay? And we'll talk more about linear system behavior as we go along. Okay, now we're going to do something that much of this stuff I know you've seen before. Some of the new parts is just vocabulary and ways of thinking about vibration that engineers do that mathematicians tend not to. So you have seen most of the stuff before. Where? 1803, right? You've done all this. And a year ago last May, in May, I taught the 1803 lecture with Professor Haynes Miller. Now, if you had 1803 last spring, I think you had somebody different. But he invited me to come. We were in the same classroom, and we taught the second order ordinary differential equation together. It was really a lot of fun. He did it. So he said, "Well, here's what we do." And then I said, "Oh, well, engineers look at it in the following way." So I'll give you what I'm going to show you is what he and I did in class that day. You can go back and watch that on video. It's kind of fun, but I'll give you my take on it today. So this is the engineer's view of what you've already seen in 1803. So we have that system, and we have that equation in motion. And the engineers and mathematicians would more or less agree to that mx double dot plus bx. But I went and looked at the webpage last night. Last spring, the person used C instead of B. Haynes Miller the year before used B. So you can't depend on any absolute consistency. But so let's start off with our homogeneous equation here. And I'm looking now for the response to initial conditions with damping. You've done this in 1803. You know that you can solve this by assuming a solution of a form A e to the st, plugging it in, gives you a quadratic equation that looks like s squared plus sb plus k equals 0. This has roots. I left out my m here. So it starts off looking like that. You divide through by the m, s squared plus b over m s plus k over m equals 0. And that's where Haynes would leave it. And he'd give you the entire answer in terms of b over m and k over m and that kind of thing. Engineers, we like to call that the natural frequency squared. And this term we modify to put it in a terminology that is more convenient to engineering. So I'll show you how that works out. When you solve this quadratic, just using the quadratic equation, you get the following. You get that the roots there's two of them. I'll call them S1 and 2. The roots to this equation look like minus b over 2m plus or minus square root of b squared over 4m squared minus k over m. And that's what you'd do in 1803. And an engineer would say, well, let's change that a little bit. So my roots that I would use for S1 and 2, I factor out, that's omega n squared. I can factor that out and it becomes omega n on the outside. And I put an omega n in the numerator and denominator here as well. So I get roots that look like So I've just manipulated that a little bit have a name for this term. I use the Greek letter zeta. It's b over 2 omega n m is the way I remember it in my brain. It's called the damping ratio. Okay. And if I say that, then the roots, S1 and 2, for this look like minus zeta omega n plus or minus omega n times the square root of zeta squared minus 1. And those are the roots that a vibration engineer would use to describe this second order linear differential equation solution, homogeneous solution. Okay, those are the roots of the equation. And when you have no damping, then this term goes away and you're left with, and I left an I out of here, I think. No, I'm fine. The I comes out of here. Okay. So for one thing to absolutely take away from today is to remember this. That's our definition of damping. We call it the damping ratio. When that's 1, it's a number we call critical damping. I'll show you what that means in a second. And when it's greater than 1, the system won't vibrate. It just has exponential decay. If it's less than 1, you get vibration, and that's why we like to use it this way. It's meaningful, it's value. You instantly know if it's greater or less than 1, it's going to change the behavior of the system from vibrating to not vibrating. Okay, so now there's 4 possible solutions to this. I'm not going to elaborate on all of them, but zeta equals 0, we've already done. You know the answer to that. Response to initial conditions, simple, we know that one. We have another solution when zeta is greater than 1. If zeta is greater than 1, this quantity here is inside's greater than 1, so it's a real positive number. And this is both roots of this thing are completely real. Okay. And you know that remember the response, we hypothesize in the beginning that the response looks like some a e to the st. So now we just plug back in. This is our st values. We can plug them back in, and we will get the motion of the system back. So for zeta greater than 1, st comes out looking like minus zeta omega nt plus or minus square root of zeta squared minus 1 times t, and you just plug this in, and x is just e to the st, but these are just pure real values. And you'll find out that the system, from initial conditions on velocity and displacement, just says and dies out. Zeta equals to 1. Then st is just minus, you get a double root, minus omega nt twice. And the solution for this, I'll write out the whole thing. X of t here is just some a1 plus t a2 e to the minus zeta omega n t. And again, it's just some kind of damp, not very interesting response, no oscillations. And then finally, zeta less than 1. And this is the only one. This one produces oscillation. And the solution for st is plus or minus zeta omega nt, a real part, plus or minus I omega nt times the square root of 1 minus zeta squared. Now I've turned around this. Zeta squared minus 1, this is now a negative number. Square root of a negative number gives me I. And now I turn this around, so this is just a real positive number. So when you get I into this answer, what does it tell you that the solution looks like? Sines and cosines, right? So now this gives you sines and cosines with a decay. This is an exponential e to the minus zeta omega nt multiplied by a sine and a cosine. And so this is the interesting part. So most of the work of the rest of this term, we're only interested in this final, in that solution. And what it looks like for this one. So for zeta less than 1, x of t is some a e to the minus zeta omega n t times a cosine omega dt omega d times t minus the phase angle. Come out looking like that. And if you draw it, depends on initial conditions. So again, a positive velocity and a positive displacement. It does this, but then it dies out. So it's very similar to the undamped case, except that it has this damping causes it to die out with time. But this right here, this is still the initial slope is v naught, and the initial displacement here is x naught. Okay. And I'm going to give you the exact expressions for this, and we'll talk about it. Another way of writing this then in terms of the initial conditions is this looks like x naught cosine omega dt plus v0 over omega d Okay, so expanding this out, this result clearly has to depend on the initial displacement and on the initial velocity. And now what's this? I keep writing this omega d. So notice in here in this solution, it's omega n times the square root of 1 minus zeta squared. So the frequency that's in here isn't exactly its omega n. It's omega n altered by a bit. Omega sub d is called the damped natural frequency, and it's equal to omega n times the square root of 1 minus zeta squared. Okay. The system actually oscillates at a slightly different frequency, and for most systems that vibrate at all, this damping term is quite small. And when you square it, it gets even smaller. So this is a number that's like 0.99 oftentimes, or even bigger than that. This is very close to 1 for all small amounts of damping. But being really careful about this, in including it everywhere, that's what this result looks like. And this little thing psi, this little phase angle here, is tangent inverse of zeta over the square root of 1 minus zeta squared. And this number turns, when damping is small, this is a very small number. And most of the time, the problems that we deal with, the damping will be small. So let's say for small damping, and by that I mean zeta, say, less than 10%, what we call 10%, 0.1. And if you have a little more, you don't care too much about the precision, it might even be 20%. Actually, if it were 0.2 squared is 0.04, right? 1 minus 0.04, 0.96, square root, 0.98. So even with 20% damping, the difference between the undamped natural frequency and the damped natural frequency is 2%. So for most cases with any kind of small damping at all, we can write an approximation which is easier to remember, and it's all I carry around in my head. I can't remember this, quite frankly. Don't try to, and I would instead express the answer to this as just an x naught cosine omega d t plus v naught over omega d sine omega damped times time times e to the minus zeta omega n t. So why do I bother to carry the omega d's along if I just said that they're almost exactly the same? For light damping, that omega n is approximately omega d. Well, you need to keep this one in here because even though it's only 2% difference at 20% damping, if you say the solution is omega n when it's really omega d, there'll be this thing will accumulate a phase error over time so that it gets bigger and bigger, this error here, because you haven't taken care of that little 2%. That 2% can bite you if you go through enough cycles, okay? So I keep omega d in the expression here. But other than that, it's almost exactly the same expression that we just came up to for the simple response of an undamped system to initial conditions. X naught cosine plus V naught over omega n sine. And now all we've added to it is put the transient decay, the fact that it decays, into the expression and change the frequency it oscillates at to omega d instead of omega n. So I'm going to try to impress something on you. If I took this pendulum and my stopwatch, measured the natural frequency of this thing, I could get a very accurate value if I do it carefully. Then I take the same object and I dunk it in water, and it goes back and forth. And it conspicuously goes back and forth, but dies down now after a while because it's got that water damping it. But I measure that frequency. And it's, you know, it's 10% different, 20% different. And I've seen people make this mistake dozens of times. You say, that's the experiment, explain why. What's the reason that that measured frequency has changed? Got any ocean engineers in the audience? All right. So why does if you put the pendulum in water, and it's still oscillating now, so it isn't so damp that it's, okay, so it's got some damping, it's dying out, and the natural frequency's changed by 15 or 20%. What's the explanation? And the answer you always get from people is damping. Why? Because everybody's been taught this thing, right? And they all then assumed that the change in the frequency is caused by damping, but damping couldn't possibly be the reason. Because with 20% damping, this thing will die out in about 2 swings and it's done. That's a lot of damping, actually. But it only accounts for a 2% change in natural frequency, not 15. So what causes the change in the frequency? No, not buoyancy. That could actually have an effect. That's actually it. I should say yes. You're partly right. There's another reason. When the thing is swinging back and forth there in the water, it actually carries some water with it. Effectively, the kinetic energy. You now know how to do vibration problems. Find the equations of motion accounting for the potential energy and the kinetic energy. The kinetic energy changes because some water moves with the object, and it's called added mass. There's water moving with the object that has kinetic energy associated with the motion, and it acts like it's more massive. It is dynamically more massive. There's water moving with it. Okay, so trying to impress on you that damping doesn't cause much of a change in systems that actually vibrate. Really, you observe the vibration. If you can observe the vibration, damping cannot possibly account for a very large shift in frequency. Okay, what's the motion look like? Let's move on a little bit here. So that's what this solution looks like. We know it depends on initial conditions. The distance from here to here will make this a time axis. This is one period. So this is tau d. That's the damped period of vibration. And we know that x of t is some a e to the minus zeta omega n t cosine omega dt minus a phase angle. We could write that expression like this. And this term, this is just a cosine. This term repeats every period, right? If it's at maximum value here, exactly one period later, it's again at its maximum. So the cosine term goes to 1 every 2 pi, or every period of motion, all right? So I'm going to define this as the value of at x at some time t. I'll call it t naught. And out here is x at t naught plus n tau d, n periods later. So this is a period, defined as period. Remember, omega d is the same thing as 2 pi times the frequency in hertz, and frequency is 1 over period, 2 pi over the period. So remember, there's a relationship that you need to remember now that relates radian frequency to frequency in cycles per second in hertz to frequency expressed in period, right? This would be tau d here, and this would be an FD. All frequency, that's for any frequency you can say that. Omega d is 2 pi, omega is 2 pi f is 2 pi over tau. So you got to be good with that. But now, so here we are, 2 peaks separated by n periods. And I want to take the ratio of x of t to x of t plus n tau d here. And that's just going to be then when I take that ratio, x of t has cosine omega dt minus phi in it. And n periods later, exactly the same thing appears, right? So the cosine term just cancels out. This just is e, and the a's cancel out. That's the initial conditions. It's e to the minus zeta omega n t, and I guess I called it t naught, over e to the minus zeta omega n t naught plus n damped periods. And if I bring this in the numerator, the exponent becomes positive. The t naught terms minus zeta omega n t naught plus those cancel. And this expression is just e to the plus zeta omega n times n t d. And the last step that I want to do to this, what I'm coming up with is a way of estimating. The purpose of doing this is this transient curve we know depends on, this is controlled by damping, by zeta. I want to have an experimental way to determine what is zeta. And I do it by computing something called the logarithmic decrement. So if I take the natural log of x of t over x of t plus n periods, it's the natural log of this expression, so it's just of an x, I just get the exponent back. This then is n zeta omega, I guess I better do it carefully, omega n tau d. But tau d is 2 pi over omega. And I get some nice things to cancel out here. So this natural log over the ratio, this is n, zeta, omega n, and this is 2 pi over omega d, which is omega n, times the square root of 1 minus zeta squared. Omega n's go away, and for zeta small, this term's approximately 1. In which case, this then becomes n 2 pi zeta. And zeta equals 1 over 2 pi n natural log of this ratio of x of t over x of t plus nt. So experimentally, if you just go in and measure, you plot out the response, you measure a peak value, you measure the peak value n periods later, compute the log of that ratio, divide by 1 over 2 pi n, the number of periods, you have an estimate of the natural frequency, estimate of the damping ratio, excuse me. Okay. So I'm going to give you one quick little rule of thumb here. So this is an experimental way that very quickly you can estimate the damping of pendulum or whatever by just doing a quick measurement. So if it happens that after n periods, this value is half of the initial value, then this ratio is 2, right? So x of t, some n periods later, this is only half as big. This value is 2. The natural log of 2 is some number you can calculate. So there's a little rule of, if you just work that out, you find that zeta equals 1 over 2 pi n 50%, not 1, times, well, natural log of 2. And you end up here with 0, do this carefully, 1 over 2 pi n 50% natural log of 2, and that is 0.11 over n 50%. That's a really handy little engineer tool to carry around in your head. So if I have an oscillator, this will end here. I can do an experiment, give it an initial deflection, and say, you know, it starts off at 6 inches or 3 inches amplitude, and you let it oscillate until you see it die down to half of that value. So let's say 1, 2, about 4 cycles, this thing decays by about 50%. Okay? 4 cycles. Plug 4 into that formula, you get about 0.025. Agree? 2.5% damping. Really very convenient little thing to carry around with you. Measure pendulum, how much damping does it have? And now, this is why I was saying most things that have any substantial amount of vibration, the damping is going to be way less than 10%. If it dies, if it takes 1 cycle for the amplitude to decrease, 1 cycle for the amplitude to decrease by 50%, how much damping does it have? 11%. So 11% damping is a lot of damping. The thing starts out here, and the next cycle it's half gone, and the next cycle after that it's half of that. And so in about 3 cycles it's gone. So if you see anything that's vibrating any length of time at all, its damping is way less than 10%, and this notion of small damping is a perfectly good one. Now I'll close by just saying one other thing. If something vibrates a lot, the damping's small. You need small damping for things to actually vibrate very much. This is vibrating. That high-pitched one, that's about 1 kilohertz. How many cycles do you think it's gone through to get down to 50% of that initial amplitude that you could hear? A few thousand? How much damping do you think this rod has? Really tiny, really tiny, okay? All right, so even though all we talked about today was single degree of freedom oscillators, I hope you learned a few things that will carry now through the rest of the term. We use all these concepts that we did today to talk about more complicated vibration. Good luck on your 2001 quiz. See you on Tuesday.